What if I told you that the fabric of our universe, the very space-time we live in, isn't as solid as it seems? What if space-time itself is just a reflection of an even deeper phenomenon? Quantum entanglement? Stick with me, because this one's about to twist your perception of reality into a pretzel. Hey there, I'm Olympia. If you're returning, thank you. You're the lifeblood of this channel. It means everything to have you here. And for those who are new, welcome to Hyperfocus. Today, we're exploring one of the most radical ideas out there, the EPR conjecture. You're going to need some coffee for this one. Ready? Let's dive in. So, think of space-time first. Einstein taught us it's a four-dimensional tapestry, warped by mass and energy. But here's where it gets strange. What if that tapestry, that geometry of space-time, doesn't even exist independently? That's where EPR kicks in. ER stands for Einstein-Rosen bridges, or simply, wormholes. EPR, on the other hand, is short for Einstein-Podolsky-Rosen, that classic quantum entanglement puzzle. Spooky action at a distance. The bold idea? EPR says that these two entirely different concepts, wormholes in space-time and quantum entanglement, aren't just related. They may actually be two perspectives of the same thing. Wild, right? But how? Alright, let me hit you with an analogy. Think of entangled quantum particles as two tango dancers, separated by miles but instantly mirroring each other's moves. Now imagine those dancers are connected by an invisible thread. EPR proposes that this thread isn't just a metaphor, it's a literal connection. A tiny wormhole linking those particles. Here's a jaw-dropping part. Juan Maldacena, a theoretical physicist, floated this idea as a way to tie together some of the deepest questions in theoretical physics. It could unite quantum mechanics, the physics of the small, the chaotic, with general relativity, the physics of the very large, like black holes and galaxies. If EPR is true, then every instance of quantum entanglement in the fabric of space-time could correspond to a microscopic Einstein-Rosen bridge. Yes, that's potentially billions, or more, of microscopic wormholes everywhere around you. Feeling small yet? But wait, let's go a level deeper. Quantum entanglement doesn't respect distance, right? If you entangle two particles, one on Earth and one on Mars, they stay connected. If space-time geometry emerges from this entanglement, does distance even matter anymore? Is space-time the stage, or just the actor, a product of these deeper quantum connections? You're probably wondering, is this pure theory, or does it have evidence? Let me tell you about black holes, those cosmic monsters that are the ultimate testing grounds for fundamental physics. Specifically, the EPR conjecture hints at resolving the black hole information paradox. This paradox asks, when something falls into a black hole and seemingly disappears forever, does the information about it vanish too? According to EPR, that's where quantum entanglement swoops in as the rescue squad. The information trapped inside a black hole may stay entangled with the particles outside it, possibly connected by, you guessed it, microscopic Einstein-Rosen bridges. So, why do physicists think this might actually work? Well, it's not proven yet. But experiments in quantum mechanics and simulations using entangled particles resemble basic behaviors aligned with the EPR concept. Theoretical support comes from string theory, a mathematical framework suggesting that the universe's smallest building blocks aren't particles, but vibrating strings. Here's where the brain sizzles. String theory's holographic principle suggests the entire content of a volume of space can be encoded on its boundary. Combine that with entanglement, and suddenly, space-time itself looks emergent, not fundamental. Some researchers are skeptical. They argue, even if space-time emerges from entanglement, EPR might oversimplify the staggering complexity involved in these systems. Others counter that simplicity is a strength. if this theory resolves contradictions between quantum physics and relativity. But here's the cliffhanger. If EPR shows us that spacetime and quantum entanglement are inseparable, if spacetime is quantum entanglement projected as geometry, then nothing we see, measure, or feel is truly fundamental. It changes our understanding of physical reality, and might even suggest new ways to probe into the vast unknowns, like multiverses, or even time travel. So, wouldn't you agree? The universe might just be stranger, more connected, and more beautiful than we ever imagined. If your mind isn't already spinning, I'd love to hear your thoughts in the comments below. If you're curious about ideas like this, make sure to subscribe, like, and share this episode. It helps the channel grow and lets us keep diving into these wild, cosmic ideas. Stay hyper-focused, and remember, in a world where space-time's geometry could be quantum entanglement, nothing is space between us, and everything is connected.